2. They're short. All right, section 4.1 is the extreme values of function. By extreme, I mean like maximum and minimum values. So there's two things we're going to look at first. That's the absolute maximum and the absolute minimum. It's really a rather simple concept. What it means is if you have a function over a given domain, then that function has an absolute largest value over that domain at a point C if f of c is greater than or equal to every other value. That means that this point right here, the function evaluated at c, is larger than any other point in the domain of that function. The absolute minimum is where this point is smaller than any other point in the domain. Whatever the domain of the function is. So here in figure 4.1, we have two functions, y equals cosine x and y equals sine x. The absolute extrema for the sine and cosine functions on the interval from negative pi over 2 to pi over 2 are as follows. Cosine has an absolute max at this point right here. Okay, that's the absolute maximum. Cosine has absolute minimums, meaning the lowest points. Maximum is just the highest point. Minimum is just the lowest point. And cosine has its minimums at negative pi over 2 and pi over 2. What about sine? Sine has its absolute maximum at x equals what? Pi over 2. This is the absolute max. It's the highest point of sine anywhere on the given domain from negative pi over 2 to pi over 2. It has an absolute minimum at the point negative pi over 2, or at x equals negative pi over 2. So here's the maximum for cosine, and then minimums. We have two minimums for cosine. If there's a tie, give both points. Okay? Excuse me. We have our first theorem, the extreme value theorem. It says if f is continuous on a closed interval from a to b, then f attains both a maximum, an absolute maximum value, and an absolute minimum value somewhere in this closed interval. That is, there are numbers x1 and x2 in the closed interval. Well, f of x1 is the minimum and f of x2 is the maximum. So we have a smallest value and a largest value than every other point in this interval. So even a single point of discontinuity can keep a function from having either a maximum or a minimum. The key word here is continuous. If you have a continuous function on a closed interval, you're guaranteed a maximum and a minimum value. If there's a single point of discontinuity, all bets are off. For example, here's a piecewise function that has a single point of discontinuity at x equals 1. Consequently, there is no highest value of this function. Because there's an open circle here, this graph can get really close to y equals 1, but it never quite gets there. So that's why there's no largest value. There is a smallest value, and that is at y equals 0. So at the point x equals 0 and x equals 1, we have a minimum value of 0. So that's what we would say here. There's no max, but we have a minimum of 0 at x equals 0 and 1. In our first problem, our first example problem, we're asked to determine from the graph whether the function has any absolute extreme values on the closed intervals from a to b. Then explain how your answer is consistent with the extreme value theorem. Okay? Do we have an absolute minimum? No. No, we don't have an absolute minimum because that's an open circle. Do we have an absolute maximum? The reason this is consistent with the extreme value theorem is we don't have a closed interval. In order for the extreme value theorem to work, you have to have a continuous function. Our function is not continuous. And we don't have a closed interval. In order for this extreme value theorem to work, this has to be on a closed interval. All right? So, definitions. A function f has a local maximum, not an absolute now. It has a local maximum at a point C when it's in the domain if f of x is less than or equal to f of c for all x lying in the domain on some open interval. Another word for local max and local min are relative max. It just means that it has to be higher than any other value in order to be a local max within some open interval around that point. So right here, here's an open interval. This is considered a local maximum. It's greater than every other function value immediately to the left and the right. Okay? This point right here would be an absolute minimum, because it's actually the lowest point on the graph. So we have an absolute minimum at A. We have a local maximum because it's not the highest. We have a local maximum at C. We have a local minimum at E. We have an absolute maximum at D because this is actually the absolutely highest value on the function. It seems obvious to me. Absolute means the highest, or absolute min, the lowest. Local means it has a horizontal tangent, or an undefined or vertical tangent. Okay? And this one's a local min because it's smaller than this point over here. Okay? This immediately to the left of it. Do you get an idea of what the difference between local and absolute? Another word for local is relative. You may hear this called relative max or min. Local is synonymous with relative, depending on what author you use in your subsequent classes. And it's important that we are able to find both of these things. Now, in order, look at the values where we have maximum and minimum values. What do these points have in common? They have horizontal tangents, don't they? Or the derivative is undefined. That's actually how we're going to identify these points we call a critical point. Well, it comes from Theorem 2. I guess I should start there. If f has a local maximum or minimum value at an interior point of its domain, and if the derivative is defined at C, then the derivative is going to be equal to C. So here where we had our local max and local mins, we have horizontal tangents. And since the derivative is the slope of a tangent line, that means that that's going to be 0. The other place where we had our absolute max right here, because we have a sharp corner right here, the derivative is undefined. So that means an interior point of the domain of a function where the derivative is either equals to 0 or undefined is going to be considered a critical point. Critical points are where the local max and min occur. Okay, critical points are where the local max or min occur. By the way, this is why in Chapter 3, for the test that we're about to take, I kept telling you, get the derivative solved and factored as simply as you can, because we're going to be finding these critical points where the derivative is either equal to 0 or undefined. That's easier to do if the derivative is factored completely and written as a single rational expression. All right, critical points without extreme values. Just because you have a horizontal tangent, that doesn't mean you're guaranteed an extreme value. This is a if-then statement, not a if and only if. Here's a vertical tangent. That's where the derivative is undefined, but it's not a critical value because it's not a max or a min. It is a critical value. It's not a local max or min. So how to find absolute extrema of a continuous function on a finite closed interval. First thing you want to do is find all the critical points. In order to find the critical points, we're looking where the derivative is either equal to 0 or the derivative is undefined. All right, then we take the largest and the smallest of these values. Okay, if we're on a closed interval, we're guaranteed the existence of an absolute max or min. In example 2, we want to find the absolute maximum and minimum values of the function on the given interval. So the first thing we need to do is we need to find the derivative. So here, the derivative is going to be equal to what?
-2.
And that means that the derivative is going to be equal to 0 when x is equal to 0. This is a critical point. We don't know if it's a maximum or a minimum value. It doesn't really matter because we were asked to find the absolute max and min. That means that I need to now evaluate this function at x equals -3, at x equals 4, and at x equals 0. So we're going to start with -3. F of -3 is the opposite of -3 squared plus 9, and that's equal to 0. F of 0 is the opposite of 0 squared plus 9, and that is 9. And F of 4, because we got to check the endpoints as well, is going to be the opposite of -4 squared plus 9. Well, 4 squared is 16. 16 minus 9 is 7. So, do we have an absolute maximum? Yes. Remember, the absolute maximum or minimum is going to occur either at the endpoints or where the derivative is equal to 0 or undefined. This point right here is our absolute maximum. So we say then that we have an absolute maximum of 9 at x equals 0. And we have an absolute minimum of what? At x equals 4. Any questions? Does that seem plausible? All right, example 3. Find the absolute maximum and minimum of the values of function on the given interval. So here we're looking at from point 8 to 7. So we have our function. The first thing we need to do is find the derivative. So this is going to be negative x to the -2 plus 1 over x. How did I get negative x to the -2? So x equal to the negative first and then take the derivative. So what that means is, cleaning this up, bless you, is that we have -1 over x squared plus 1 over x, and we've got to set this equal to 0 in order to find the critical points. Well, that means that 1 over x squared, first thing I should probably do is get a common denominator, huh? So I'm going to multiply this by x over x. And that's going to give me x minus 1 over x squared equals 0. Because this already had the common denominator, it's -1. This is 1 times x is x. That's why this came like this. So your critical points are where the derivative is equal to 0 and where the derivative is undefined. So we have critical points at x equals what? Well, this derivative is equal to 0 when x is equal to 1, right? And it's undefined when x is equal to 0. So what we need to do now is go back to, why can we disregard this one? It's not in the domain. So if you have a critical point that's not in the domain that you're given, you don't have to worry about checking it, because we're wanting to know the absolute max and min on this interval. So now we have to go back and we have to check the value of f of what? 0.8? So that's going to be 1 divided by 0.8. I think that's 80. I don't know. Plus the natural log of 0.8. And what do we get here? Plug it into your calculator, give me a decimal approximation. This is approximately what?
One.
0.1 divided by 0.8 plus the natural log of 0.8.
I mean, it's just 1. Well, it's just 1.02.
Okay, thank you. 1.026.
I don't know how far you want.
Well, I needed more than the 1 because
Okay.
f of 1 is actually 1.
Okay.
And then we've also got to check f of 7. So that's going to be 1 divided by 7 plus the natural log of 7. And that's approximately what?
0.987.
Okay. Well, then that means that we have an absolute maximum. That's a S. Of about 1.026 at x equals 0.8, and we have an absolute minimum of 0.987 at x equals 7. Yes? Thank you. Well, that changes things. Oh, my calculator.
Oh, yeah. I think
Make sure you close your parentheses after.
I think I hit the log button.
It's 2 point what? 2.09. Okay, so we have an absolute maximum of 2.09 at x equals 7 and an absolute minimum of 1 at x equals 1.
Yeah, I hit the log button.
Okay, don't do that. All right. Any questions? Nope. That's absolute extrema. So stop this.